Hello. So today we're going to talk about the production theory. Okay, so this is the chapter 5 in the textbook. Okay, so the production theory is very symmetric to the consumer theory. It's just another aspect of economics, right? So we're talking about the firms or the producers of the consumption goods. Okay, so something different from the consumer theory is that in the consumer theory we can choose some non-negative amount of goods to consume, right? Either zero or positive amount of goods. So here in the production theory, especially in this textbook, we're gonna see that sometimes we might take some negative amount of goods to be our inputs, okay, and to help us to produce some amount of outputs which are denoted in positive, okay. So there is some signs with positive or negative. So it's a little bit more complicated than the consumer theory, but there should be no problem with further understanding that. Okay. All right. So today we're gonna first introduce or define the production set as we did in the consumption set, right? So that'll be including all the feasible productions. And then we're gonna define a transformation function, okay, which is defined on the production set. And later we'll introduce the production function, okay, and we'll see that if we only have one output and the production function is enough, okay, so we don't need transformation function in general. And then later we'll compare or we'll connect the transformation and production functions and make some comparisons between those two functions and give some example. Okay, and finally we will follow the textbook and introduce several assumptions that we give for those production sets as their properties. Okay, when we analyze some production problems. Okay, good. So now let's begin with the first definition. Okay, so again we have the same L-dimensional commodities or goods. Okay, so a production vector okay, this is also known as input output or net output vector, okay, or a production plan. So it is a vector, let's say this little y, okay, so it's L-dimensional. So here it'll be an element in the real of L, but we do not longer assume that this is positive or R plus L, right? So here we simply assume that to give it any real number in the L dimension. Okay, so this describes the net outputs of L commodities or goods from this production process. Okay, so and we adopt the convention that positive numbers denote the outputs and negative numbers denote the inputs. Okay, so positive are the outputs, so we use the signs to distinguish the outputs and inputs for the productions. Okay, so this is something different from the consumer theory. So positive and negative numbers for the inputs, okay, for those L dimensions. Okay, good. So let's have example, which is the textbook for 5.b.1. So it's saying that suppose here we have 5 dimensions, okay. Let's assume that this little y will be -5, 2, -6, 3, and 0, okay. So this means that 2 and 3 units of good 2 and 4, they're produced. Okay. And 5, 6 amount of good 1 and 3 are used. Okay. These are input or used for the production. Okay. And 0 amount of 5, so good 5 is not used or not produced. So it's not produced or not used in this process. Okay, so that'll be a simple example for this production set. Okay, good. So so that'll be element in the production set. Okay, so we're gonna define the set of all those vectors, production vectors, that constitute feasible plans for the firm is the production set. Okay. And which is written as capital Y. So therefore it has to be a subset of RL. Okay. So we say that any element in this Y, it is possible or feasible. Okay. And if Y is not in the set Y, and that is not possible. Okay. Good. So, and sometimes it might be more convenient to describe the production set using some function, and we're gonna call that as transformation function. Okay, so transformation function. So this should be the second point that we're gonna discuss for today, right? Okay. So what is a transformation function? So a transformation function, okay, so let's say for some set Y, we just saw, right? So that'll be some for element Y in RL. So what are those little Y's? We're gonna let the function taking this little Y to be less than or equal to 0, okay? And Fy, it is strictly 0 if and only if Y is an element of the boundary of capital Y. Okay? So the set of boundary points of capital Y, therefore, is those little y's in RL, where this Fy is exactly 0. Okay? This boundary is called transformation frontier. Okay. So this transformation function is sort of a general version of production function that we're going to define shortly. Okay. So the reason we have this transformation is because that we could have multiple outputs here in the transformation function. Okay, but in production function that we're gonna see shortly, we're gonna only have one specific output. Okay, in the production function, but not here. Okay, so let's use a little figure to further show this idea of this transformation function. Okay. So okay, we're gonna have the space of y2, y1 and y2, right? So we might have some negative numbers, right? So most of actually the main part is is negative. Okay, so Okay, so let's suppose we have some curve. Okay, all right, let's have a curve going through the region where this would be the set of y, where fy is exactly 0. Okay, so this is going to be the transformation frontier. Okay, good. So all those area to the left or to the down, to the below of this curve, that'll be the capital Y. Okay, where this y such that fy is less than or equal to 0. Okay. All right. Okay, so this is a example of the transformation frontier. Okay. All right, and further, if we want to assume that this f function is differentiable, okay, then if the projection vector, some y bar, satisfies that fy bar is 0, then for any two commodities, then the ratio of those partial derivative of this fy bar with respect to either yl and yk, so that ratio has to be the slope of the tangent line to this curve, right? So let's suppose if f is differentiable and some fy bar is 0, okay, then for some l and k, we have some marginal rate of transformation, okay, l and k for some y bar. So that's going to be the partial of l partial yl over partial fy partial yk. Okay, so this marginal rate of transformation is going to be, let's have some tangent line. Okay, okay, this is not straight. Let's have a straight line here. Okay, and suppose this would be the tangent point. Okay, and we're gonna have a gradient of f of y, which is orthogonal to this tangent line. Okay, where we have this y bar. Okay, so the slope of this tangent line will be the negative of MRT 1 to y bar. Okay, good. So and in addition, okay, this marginal rate of transformation is just a measure of how much the output of good K can increase if the firm decreases the output of good L by one marginal unit, right? So from the assumption of fy bar is 0, we can differentiate, we can total differentiate and get partial fy yk dyk plus partial fy bar yl dyl to be 0. So the slope of the transformation frontier at y bar, that has to be exactly the minus of MRT. Okay. All right. Good. So that'll be that was the transformation function. Okay. So that was, in some sense, that was quite general because we could measure, for example, this marginal rate of transformation for good L or for good K, but either of those can be input or output, right? We can just simply measure them in terms of the net output, okay? So next, we're gonna introduce another notation or another representation, which is the production function, okay? And then after finishing that, then we're able to compare the production function with the previous transformation function, okay? Good. So I think this will be the third part for today, right? Okay, good. So the third one, which is the production function. Okay. So let's say this vector Q, including from Q1 up to Qm, okay, so we're gonna require that this Q has to be non-negative. So this, we let this to denote the production levels of the firm's M outputs. Okay, so those are strictly positive or zero outputs. Okay, and then we're gonna use the Z vector from Z1 up to ZL minus M because we're gonna have in total L dimensions, but we have M for Q, so therefore we have L minus M to denote the inputs. Okay, so those are also positive numbers, but later we'll use the minus sign in front of Z. Okay, so to denote that those Z's are inputs. Okay, but here those are just the absolute values, or those are just the positive numbers or zeros. Okay, so we're gonna let those to denote the amounts of L minus M dimension of inputs. Okay, so this is the convention that the amount of input ZL used is now measured as the non-negative number. So that is just the absolute value, right? So, okay, so we count all goods not actually used in the process as inputs. Okay. So, and normally we can just regard each firm to just have one single output. Okay, so to easily model this problem, but you can't always model the problem as multiple firms and the individual firm is producing just one single output. Okay, so let's say one single output technology that is described using a production function. Okay, to describe one or single output, let's say, following the textbook, single output technology. Okay, to describe that, we use production function, which is called F, taking all those Z's. Okay, and it's gonna give us the maximum amount of Q that can be produced. Okay, so Q is just the ceiling, right? So we can not exceed Q, but we can produce less than amount of Q. So it can be produced using Z1 up to ZL minus 1 inputs. Okay, so for example, if the output is exactly this L, capital L, good, then assuming that the output can be disposed at no cost, right? So we can so either the firm can waste some part of the production, or the production can be disposed, okay, randomly, so arbitrarily. The production function, okay, so f gives, then f then defines this production set, okay, gives rise to the production set. So the production set is going to be those elements which are the inputs from Z1 up to Z minus Z L minus 1, and this Q, that'll be the maximum amount of output, right? So where this Q is the maximum, okay, and the actual production, that'll be F taking Z1 up to Z L minus 1. Okay, so this Y has to be less than or equal to 0. Okay, and this this might look very familiar to you, right? So, and we have seen this before in the definition for the transformation function, right? And it turns out that those are essentially the same thing. Okay, so this has to be less than or equal to 0, and where all those inputs Z1 up to ZL minus 1, those are just the absolute values, which have to be positive or equal to 0. Okay, good. But we'll connect this to the transformation function. Okay, no worries. So now let's gonna still focus on this production function. Okay, and if we can hold the level of the outputs fixed, then can define some other rates, okay, called marginal rate of technical substitution. So marginal rate of technical substitution, which is MRTS. So this rate is much more common to see, right? So it's MRTS of input L and K at some level Z bar. Okay, so that's gonna be MRTS LK at Z bar. So that'll be partial F Z bar partial ZL over partial F Z bar partial ZK. Okay. And we're gonna have the similar interpretation as the previous rate, okay, we defined earlier. So this number or this rate, it measures the additional amount of input K that must be used to keep the same output level Q bar at FZ bar when the amount of input L is decreased marginally. Okay. All right. So so next we can have an example on this production function. Okay. It's the very classical Cobb-Douglas production function. So the Cobb-Douglas production function with two inputs is given by this f z1 and z2, where z1 to the power of alpha and z2 to the power of beta, and where those are non-negative parameters. Okay, so, and it's not difficult it will be actually very easy to find the arithmetic TS of the Cobb-Douglas function at z is z1, z2. Okay, that's gonna be alpha z2 over beta z1. Okay. All right. So before we go to the properties of production sets, so remember that we're gonna, something important is to compare or to try to connect the production function and something we defined earlier, which is the transformation function. Okay, so that's gonna be the number 4 for today. Okay, good. Okay, so this would be talking about the transformation f and little f. Okay, we should write the info name. This is not, it's nothing here. Okay, so transformation and production function. Good. Okay, so now let's suppose, okay, we have a firm that is producing a single output. Okay, so that single output is just Q. Okay, and we're also gonna assume for a Cobb-Douglas function. So we will have this Q to be the maximum output, right? So okay, Q. Now we're gonna use this Q to denote the output. Okay, so this Q is less than or equal to. So this F, that would be the maximum amount of output. Okay, so here we're changing this in the other way around. So be careful. So this F x1 is just for example this purpose of this example. Okay, F1 x2, that's gonna be in Cobb-Douglas. That'll be x1 alpha and x2 beta. Okay. So this f x1, x2 is the maximum amount of Q can be produced within the technology of this firm. Okay. So next, the production possibility or simply the production set Y, okay, that'll be including is the set of all those vectors, right, of those productions vectors, where we have little y, okay, to be, now we're gonna put minus in front of those inputs, okay, and we have this Q, which is the actual output, okay, and this Y has to be a subset of R3, okay, such that the above inequality holds, okay, and essentially we're talking about this capital Y to be the set of this little y, where this Q is less than or equal to f x1, x2, okay. So we must notice that the vector has negative signs on x1 and x2 because they're inputs, as we mentioned, right? And this output Q, it is positive as the output, okay? So that's the production function, okay? And we have seen this in the definition of the production function and in the example of Cobb-Douglas function, right? So An alternative, or actually it is an equivalent way, okay, equivalent way is to use this transformation function, okay. So this capital F, that'll be a map from R3 to R, okay, to R1. So in this example, it's gonna be F little y to be exactly this Q minus x1 alpha, x2 beta, okay. So again, using this notation with the transformation, we're gonna have our, to define our capital Y again, that'll be the set of all those little y's where we have f of y to be less than or equal to 0, okay. So we can see that they're talking about exactly the same thing, it's just using different notations, right? So where f of y less than or equal to 0 implies the first inequality to hold. Okay, that we mean that this f, little f, has to be the maximum amount that we're going to produce. Okay, we cannot exceed q, at the q cannot exceed the maximum amount of little f, right? So this would be a fairly simple way to interpret when there is only one output for just using the production function, right? So the concept of the transformation function, it'll be useful for allowing us to think about the productions that might use multiple inputs and use multiple outputs, right? Okay, so that would be the links between the equivalence, or the links between those two different representations of the production. Okay, good. So lastly, we're gonna follow the textbook again and discuss several properties in production sets. Properties of production sets. Okay. So the first assumption, y is now empty. Okay, this is very straightforward. So it simply says that the firm has something it can plan to do, right? So otherwise, we don't have any problem to solve, right? So the second would be that this y is a closed set, okay? So it means that this set has to include its boundary. And that'll be useful later for us to prove some mathematical results. So the third one is called there's no free lunch. Okay. So this means that mathematically, okay, suppose this little y is in the capital Y, and let's, for example, if this, suppose that this little y is positive or 0, so that y does not use any inputs, and we say that this is not possible. Okay, so this no free lunch is satisfied if this production vector cannot produce output either. Okay, so that is whenever y in y and y to be positive equal to 0, then this firm cannot do anything. Okay, so there will be no output. So it means it is not possible to produce something from nothing. Okay, it is not possible to produce something from nothing. Okay. Okay, so this looks like a reasonable assumption, right? But it's just economics, right? It might not be true, like for example, maybe in other disciplines, but we don't know. Okay. So things might come from nothing, right? But we just assume that we have to use some inputs to get some output. Okay. All right. So that'll be the third one, no free lunch, and the fourth would be called the possibility of inaction. Possibility of inaction. So here it's also a simple idea. It says that 0 as element of y, so shutdown is possible. Okay, so a firm can simply choose to close the firm and just choose to not produce anything for some time period. Okay, so that'll be okay. All right, so that's the number 4. Okay, and before that we should have, right, so we should have some picture for number 3. Okay, let's move this a bit downward. Okay, so we're gonna use this picture on the textbook for 5.B.2. So we're gonna have, okay, 2 examples. So this will be y1 and y2. Okay, so if we have the capital Y to be the boundary to be this, okay, and all the shaded area is this capital Y. So this would be the case violating no free lunch assumption, right? So because we were using 0 amount of y1 to produce a positive amount of y2, right? And that was not allowed by this assumption. Okay. However, if we have something like this, okay, if we simply start this, okay, let's use this, start this from exactly 0, that'll be fine, right? Because here we use 0 amount of y1, but we produce 0 of y2. So we have to take some negative level of y1. So negative means that this is called input. So we have to put some input for y1 to get some amount of positive y2, right? Okay, good. So let's continue on the inaction assumption. Okay, yeah, and for the next. So the next will be the assumption of called free disposal. Okay. So, and this is also easy to understand that the firm can just freely dispose anything. Okay, no matter it's the input material or it's just the output, the firm is okay to just dispose anything. Okay, so mathematically, so if y is in the set and y prime is less than or equal to y, so that y prime produces at most the same amount of outputs using at least the same amount of inputs. Okay, then y prime is also in y. Okay, so this means that it's okay to freely dispose. Good. So okay, and alternatively, there'll be an alternative definition that'll be y minus some subset of RL positive. That'll be still a subset of y. Okay. So from a figure, say this is y2, y1, okay. For example, if we have this boundary of y to be like this, okay, and let's say this is the y, okay, on this boundary. So all those area to the left and to the down of this y, that'll be the set of y, little y's minus r2 plus. And those are also feasible, okay? Good. So that was the number 5, free disposal. Okay, let's continue the number 6, which is called irreversibility. Okay. Good. Very long word. So now we're gonna suppose that y is in y and y not 0. Okay. Then this irreversibility says that simply the negative of y, this will be the negative of vector, which is not in y. Okay. And as we mentioned in the beginning, for example, some picture like this. Okay. So if we have, this is sort of look like a concave function. Okay. And go through the origin. And we must not have any point if we make a symmetric one with respect to the origin, then this has to be outside of y, right? For example, if we simply have a symmetric one to this, this has to be out of y, right? And this is true for any other points in this set. So we have to assume this is called irreversibility, and it intuitively it says that it is impossible to reverse a technologically possible projection vector to transform an amount of output reversely into the same amount of input that was used to generate it. And this is sort of like the increase of entropy in physics, right? And this is a very interesting assumption. Okay, so good. So that'll be the number 6. Okay. All right, so let's continue. And up to here, okay, so from 1 up to 6, those are just some normal assumption that we might see, okay? So from 7 up to 7, 8, 9, okay, so this would be 9, right? So from 7 up to 9, those three that are just some possible assumptions we might have or we might not have, okay? But normally we will have from number 1 to up to 6, okay? So maybe. So those are always, okay? Good. So number 6 assumption says it is called non-increasing returns to scale. So it includes either the equal version or the decreasing version of return to scale, right? So the production technology Y, capital Y, exhibits non-increasing return to scale if for any Y we have, if we multiply this Y by some alpha, it has to be still in this Y if for, okay, not if, for all alpha between 0 and 1, okay? So in other words, any feasible output vector can be scaled down, okay? And it is also included in this Y. So correspondingly, number 7, 8, right? 8 would be non-decreasing returns to scale. So we simply copy and paste. And change this to be greater than or equal to 1. And that's done, right? So here, in other words, this vector can be scaled up, right? So that's called non-decreasing return to scale. So, and of course, last one will be the constant return to scale. Okay, so that'll be if y in y, this implies alpha y. Also in y for any alpha. Okay, so we don't have any restriction on this alpha here. Okay, and geometrically, this capital Y here, it'll be a cone. Okay. All right, so before that, now let's have a look on some examples on the textbook for figure 5.b.5. Okay, that'll be the examples for non-increasing return to scale. Okay, so y1, y2, if we have the boundary of this capital Y to be something like this, sort of concave. Okay, this is not good. Okay, and then like this. Okay, so if we have any point, for example, this would be little y, and we want to connect this with the origin, then any points in between. So this means that alpha y, this alpha is between 0 and 1. Right? It's also within this y. So this would be the case where non-increasing return is satisfied, right? But here also we can notice that it's not satisfying the non-decreasing, right? Because if we also choose another point, then connect this with the origin. For example, we can still use this y, right? But if we connect this and further extend this out to have some alpha greater than or equal to 1, then this is not in y. Okay. All right. So that'll be the first example. Okay. So can we give some counterexample on the other way around? And yes, we can do that. So okay, for example, let's have sort of a convex boundary on this. Okay, good. So if we have, for example, let's take a point, and if you want to have this connection to the origin, then this alpha y, when alpha is between 0 and 1, this is not in y. Okay, but if you further extend, let's change this color. If you further extend this, okay, where this alpha is greater than or equal to 1, this is in y. Okay, so those are examples where we satisfy the non-increasing return, but not the first one is satisfying the non-increasing, but not satisfying the non-decreasing. The second one will be the other way around. Okay, good. So and up to here we have introduced several assumptions that we normally see, right? And we have some other assumptions, okay? you could have a look on the textbook. Okay, so where we have number 10, additivity or free entry. Okay, and number 11, which is the convexity. Okay, and so those would be some other assumptions that we maybe we can introduce later when we meet those requirements or the assumptions later in the real problems. Okay.